Now once we have done that, now what we can do is, now we can take special cases and see the evolution of the system under special conditions. So now we can take special cases, right? And what I mean by special cases is, so let us say that x10 is equal to x20. So both the masses have been displaced by the same amount in the same direction, right? And then the system is left to evolve. So if that is the case, then this would imply that x0 is basically 2x10 and x0 prime is 0, right? And in that case, the equation of motion is simply x of t is equal to 2x10, so some amplitude cosine of omega 0 t, right? Or I'll write it omega minus t. Right? What this means is, if the initial condition is like this, if both the masses are displaced by exactly the same amount in the same direction, then they both keep oscillating together, right? The amplitude is 2x10, they both oscillate together with a single frequency omega minus, right? So that way they act as one oscillator, right, which is making oscillations at this natural frequency omega minus, and we know that omega minus is nothing but omega naught, it's just p over m, right? Okay, so this is our case 1. Case 2 would be when x10 is minus x20. So mass 1 is displaced by some amount x1 and mass 2 is displaced by the same amount, however in the opposite direction, right? So basically that means they are both stretched in the opposite direction, and then this initially the coupling spring is compressed, right? Okay, if that is the case, then again what we can see from here is, in that case my x0 is 0 and x0 prime is nothing but 2x10, and that means the equation of motion or the motion is described by this equation. So similar amplitude cosine of, however now omega plus t, right? So in that case, then basically the masses are still oscillating with a larger higher frequency now. So not their natural frequency, they're still acting as if it's a single oscillator, right, with a characteristic frequency omega plus. However, this frequency is larger because it's omega naught square plus 2 omega k1 square, right, and with some amplitude. And if you look at this motion, what this motion will describe us is, the masses will be either going away from each other or coming towards each other, right, all the time. So the motion is out of phase. So this will give us in phase oscillation, and this will give us out of phase oscillation, right? So, and I guess you have seen something similar when you do this coupled pendulum experiment in your lab. Right? Okay. An interesting third case can also be seen, right, and which is again related to this initial conditions. So the third case could be that x10 is a, right? So let's say we have displaced this mass by some amount, whereas x20 is simply 0. So not displacing the other mass. So one oscillator is at the equilibrium position initially at t equal to 0. Another one is described by certain amount, right? So then how the solutions look? So then x of t is basically the cosine of omega minus t. X prime t, now we have both the solutions present, is again a cosine of omega plus t, right? Where just for the sake of completeness, let me write down omega minus is omega naught and omega plus is omega naught square plus 2 omega q1 square, right? Okay. So these are the two solutions, right, of the system where this is the initial condition, right? And now what we can do is, now I can find out how the oscillators actually make the motion. This is the motion of the normal coordinates. Now we want to find out what is how in lab we will see the system to move. So we need the equations in terms of x1 and x2, and we know what are x1 and x2. x1t is nothing but x of t plus x prime of t divided by 2. This is from the definition of the normal coordinates that we used earlier. So this is the definition. Then this basically becomes a by 2 cosine of omega minus t plus cosine of omega plus t. So this is then my solution for x1t. I can write down the similar solution for x2t, simply cosine of omega minus t minus cosine of omega plus t. Okay, anyway, so let's try to let's put it in slightly more compact form. So for that, what we'll do is we can describe, or we can write down omega minus as something omega plus omega minus by 2 minus omega plus minus omega minus by 2, right? So it's just a rearrangement of the same term, right? It's exactly the same thing. We can write omega plus also in the same form, omega plus omega minus by 2 plus omega plus minus omega minus by 2. Rearrangement, it's just a algebraic rearrangement, nothing else. Put this back here. We can write down now x1 of t, and now this is small x1, so this is basically describing motion of mass 1, a by 2. So we are trying to write it in terms of cos A plus cos B. So cosine omega minus was this entire term. So omega plus omega minus by 2 minus omega plus minus omega minus by 2 plus cos of same omega plus omega minus by 2 and plus omega plus omega minus by 2. Right? So this is the same term, we have done like this. And now what this is? This is cos of A plus B and cos of A minus B, right? So cos A plus B is cos A cos B minus cos A cos B plus sin A sin B. Cos A minus B is cos A cos B minus sin A sin B. So if we sum these two, what we are left with is something like this: 2 cos of cos of A and cos of B. So cos A will be then omega plus omega minus by 2 cos omega plus minus omega minus by 2, right? So what we have done is we have taken this as A and this as B, right? And then if you can solve it, you will see that you get this expression. So you cancel it out, right? And we can write it down as I'm not going on. This is straightforward. And now, if you want, we can simplify it further. It doesn't. I mean, simplify in the sense we can choose other variables also to just write down in slightly more compact form. So this is then x1 of t. right? Let me just check if I want to rearrange it in any other way. No, probably I'm okay with this. Right. Yes, and similarly, I can also write down. You can follow the exactly same scheme, and what we will get is we will get omega plus omega minus by 2 and sine of omega plus minus omega minus by 2. So that is exactly for x2. So starting with the normal coordinates and using the initial condition, we can write down the solution for these two particles or these two oscillators, right? And one of them is a cosine function of this coupled frequency. Now they are not the natural frequencies of the masses as such. They are not simply square root of k by m, right? So we'll have this omega plus omega minus, similarly omega plus omega minus. However, the solution is then written in this form. So the oscillation frequency is now a combination of these two natural frequencies or the normal modes of my system, right? Okay. Now to relate it to the problem that you have tackled during your laboratory sessions is, let us say if this K1 is much less than K, right? Or on the other hand, or the same thing that we are saying is omega naught or omega K1 is much less than omega 0, right? So that means if, let's say, the oscillators have some characteristics, however the coupling is rather weak, right? So this is under weak or weakly coupled oscillators. So compared to their natural frequency, the coupling is rather weak. So if this is the particular case, then what we can do is we can simplify this omega plus term, the higher frequency, right? So we know that what was this? This was basically square root of omega naught square plus 2 omega square k1, right? So now we can kind of simplify this. We can take the omega naught out, then this is 1 plus 2 omega k1 square over omega naught square. And since omega k1 is much less than omega naught, this is a very small term. So we can do a binomial expansion, keep the first two terms, forget about the higher order terms, and we can make that approximation, and this will then give us 1 plus omega k1 square over omega naught square, right? And what I want to do now is write it down in terms of, again, two frequencies. So omega naught plus, let me write it down as 2 of epsilon, right? So I am simply writing this as this, and what that means is that I have written 2 of epsilon is equal to basically omega naught omega k1 square over omega naught square. Right? So I have simply used this term, and I can see that this term is much smaller compared to omega naught itself, because this term is very small, right? Omega k1 is much smaller than omega naught, so the square term will have even lesser magnitude, multiplied to omega naught will be a much lower frequency compared to omega naught. However, anyway, I can write down now omega plus, instead of that square root term, I could write it down in terms of these two frequencies, omega naught, the natural frequency of these oscillators. So under weakly coupled system, there is a slight change in the omega plus, and omega minus remains more or less the same, right? Omega minus was simply omega naught, right? And if this is the case, then now my solutions take a slightly different form. So now x1 of t is a cosine omega plus omega minus, and omega minus was already omega naught, right? This we already know. So this plus omega naught, so 2 omega naught plus 2 epsilon. So this will be simply omega naught plus epsilon of t and cosine omega plus minus this thing. So this minus the same. So 2 epsilon t, again 2 will get cancelled, will go out. So this will be simply epsilon t, right? So again, in the weakly coupled case, where we know that the coupling frequency is much lower compared to the natural frequency of these oscillators, I can write down my solution in this form. Right? Similarly, I can write it down for the other case. x2 of t is then a of sine omega naught plus epsilon t sine epsilon t, right? And so these are the two solutions for my weakly coupled oscillator. What this tells us is that now both the systems are going to oscillate. So if we look at their time evolution, they are going to show us a periodic change in the amplitude. They will start with the maximum amplitude A at some point of time, and however, rather than controlled by a single periodicity, which was omega naught in the natural case, this will be now there will be two frequencies governing the motion, omega naught plus epsilon and epsilon with the same functional form. Now, of course, if epsilon is very much smaller, which is established here, for which this solution is valid, then what we have is we have oscillations which have very different time scales, right? So one is this time scale governed by omega naught basically. Another one is this one. This is fast compared to, much faster compared to this one. This is a much lower oscillation. So if I try to plot the time evolution, let's say x1 t, right? At t equal to 0, this is at a. I know that, right? We started with this assumption, or we started with this initial condition, sorry, not the assumption. And now what happens, right? So first of all, let's forget about this faster term, let's look at this slower term, right? This is cosine of epsilon naught t, epsilon is some frequency parameter. So if this term is not there, the amplitude is going to simply follow this cosine function and go like this. Okay. Where are the zeros? So it starts with a at t equal to 0. At t equal to pi by 2 epsilon, this thing will go to 0. Again at t equal to 3 pi by 2, so at t equal to pi by epsilon, this is going to be maximum in the other direction, so minus a. And then at 3 pi by 2 epsilon, again this will be 0, and then at 2 pi by epsilon, again there will be maxima, right? 2 pi by epsilon. So we can sort of see the behavior of this function. How about the behavior of this function? So this frequency is much faster, right? Omega naught plus epsilon. So this is going to follow the exact same pattern, and correspondingly it's also going to change the amplitude. However, with a much faster cycle, with a much higher frequency, right? So in that case, what will happen is, by the time this makes a change, the change here will be very small. So within this, by the time this function actually takes the amplitude from maximum to minimum, this function would have already taken the amplitude between the maximum minima cycle multiple times, right? So we can show this. So this is just the other envelope of this. And now, so what this function is going to do is, this is going to again start from here. However, this goes much faster to 0, turns back, comes up, turns back, comes down, then again starts to go rise, fall, rise, fall, follow the motion. So the amplitude is basically bound between plus minus a, however not controlled by only one frequency but two frequencies. One is a much faster one, other is a much slower one, right? So then let's say this one, let's say this solid curve is my omega 0 plus epsilon, right? Whereas this change in the maxima of the amplitude, right, which I depicted with the dotted line, right? Right? So this one is then basically omega with the frequency omega, right? So this is how the oscillator is going to behave in real time, right? And this envelope or this frequency epsilon is termed as beat frequency, and this phenomena of having the amplitude slowly going to 0 and then again catching up is termed as beating, right? So what we see here, these points, this is called beating, and normally this is observable in case of sound waves, right? So if sound waves of very close frequencies are present together, then one sees this kind of beating. It's the exact same phenomena which is happening here in case of the oscillators, because again the oscillators are coupled by this weak coupling force, right? And the beating is happening because if you look at the solution, right, if you look at our normal coordinate or independent coordinate solution x of t, what we had was, we had it something like this: cosine of omega plus omega minus by 2 plus cosine of omega plus no, not this one, right? What we had was, yeah, omega plus t plus cosine of omega minus t, right? And in this weakly coupled regime, what we have seen is omega plus is not very much far away from omega naught, and omega minus is actually omega naught, right? So that is why we have seen this kind of beating, because we have two oscillators which are, we have two frequencies which are coupling and which have more or less the near about same magnitude, right? Okay. So anyway, this is the analysis for these coupled oscillators. We have done it for this system. Of course, as I said, for the simple pendulum system also, this the analysis was exactly the same. Now, the last interesting feature or the important feature that we need to see from here is that if you look at these two solutions, x1 and x2, so first of all, at t equal to 0, x1 is at A, x2 will be at 0. So that means, to begin with, all the energy is stored in the motion of mass 1 and none in mass 2, which is again true because we have only displaced mass 1 and not displaced mass 2, right? However, with time, that energy gets shared. So it's not that if you only displace this one, only this oscillates. Because the coupling is present, it starts transferring energy to the other oscillator, and they keep sharing this total energy into each other, right? The way they share it is so again, energy sharing will be, it's more complicated compared to a single harmonic oscillator, because now you have kinetic energy and potential energy of both the oscillators. Nevertheless, the slowest one governs the behavior. So what you can see is, when x1t, so at this point, when the amplitude of x1t goes to 0, actually at that location, epsilon equal to pi by 2, the amplitude of x2 will be maximum, right? And similarly, when the amplitude of x1 is maximum, the amplitude of x2 will be minimum, right? So, and in between, of course, at any other given time, the energy will be shared between both of these, right? And this you have nicely seen in case of the experimental demonstration, that if you only oscillate swing one pendulum, slowly the other pendulum starts to swing. The first one comes to almost a rest, and the other one makes the maximum amplitude oscillation, and then again it transfers the energy back into this thing. And this phenomena is termed as beating, which we have described here.